Let's find the electric field due to an infinite plane of charge in the xy plane, and let the charge density be rho sub s coulombs per meter squared. So this is looking down on the plane of charge from the positive z-axis. This is looking edge on at the plane of charge, looking down the y-axis with the positive y-axis into the plane of the page. This is the general form of the electric field intensity in Cartesian coordinates, but most of these terms will disappear because of the Cartesian symmetry. If we place a test charge above our plane, there won't be any net force in the x and the y direction because the charges are infinite in the x and y directions. The only force that the charge will experience will be in the plus z direction. So there's no x component or y component to the electric field intensity. If you move the test charge just in the x direction, the force will not change because the infinite plane of charge still looks the same below it. And similarly, if you were to move in the y direction. So there's no x or y dependence on the electric field intensity. So at most, the electric field intensity will depend on z, but shortly we'll see it doesn't even depend on z. But we can't clearly make that argument at this point. You have the same situation for z less than 0, except that the direction of the force is flipped. It's now in the minus z direction. Let's now apply Gauss's law, and we're going to pick a Gaussian surface that matches the symmetry of the electric field intensity. So we pick a Gaussian surface whose top and bottom is parallel to the xy plane and whose side is perpendicular to the xy plane. So no electric flux is going to go through the sides of our Gaussian surface. If the top surface is at z and the bottom surface is at minus z, the electric flux density field will have the same magnitude on the top and the bottom, but on the top it will point in the plus z direction, on the bottom it will point in the minus z direction. On the top surface, ds will be dx dy in the plus z direction, and on this bottom surface it will be dx dy in the minus z direction. So the integral over this Gaussian surface will be the integral over the top plus the integral over the bottom plus the integral over the side. But as we already argued, no flux goes through the side, so this integral of d dot ds over the side will be 0. Let's give a surface area here of S for the top and bottom surfaces. The charge enclosed will be the area of this intersection of our Gaussian surface with the xy plane times the surface charge density, and that will equal rho sub s times s. So over the integration on the top for d, we make this replacement. For ds, this replacement. For the integral on the bottom, for d, this replacement. And for ds, this replacement. The electric flux density fields are constant on these surfaces, so they can be moved to the left of the integral. The az dot az will just be 1. And this minus times this minus is a plus, so both these integrals end up being the same, and this integral here of dx dy over the surface will just be the surface area S. We can divide both sides by S. Solving, we find that the electric flux density field at location Z is rho sub S over 2. And we see it does not depend on Z. Z could be 1 meter or it could be 10,000 kilometers. You would have the same electric flux density field. So when Z is greater than 0, the electric flux density field is rho sub S over 2 in the plus Z direction. And when Z is less than 0, the electric flux density field is rho sub s over 2 in the minus z direction. And this result should make sense to you. You know, if you have a charge density of rho sub s, coulombs per meter squared, there's rho sub s coulombs per meter squared of electric flux emanating from it. And if you have an infinite plane, half of that electric flux will emanate in the plus z direction, and half will emanate in the minus z direction. So you should have this mental model now that if given an infinite plane of charge, you can essentially just write down the electric flux density fields.